Good morning students, welcome back to session 6 of linear transformation classes. So in the last class you have studied one of the canonical form, which is the triangular form. So the criterion for the existence of a triangular form is all the eigenvalues of the linear transformations lies in a field F. Okay, so if T belongs to E of V, then T has a triangular canonical form if all the eigenvalues of T lies in a field F. All the eigenvalues of a T or characteristic roots of T lies in a field F. Okay, so but we know that every transformation definitely has a eigenvalues, those lies in field F. Say if they do not lies in the field R, then the field R can be extended to the field C where all the roots are lies in C. Therefore, every transformation can be bring it to triangular form. Okay. Next, let us move on to the next canonical form. Before that, let us take up one important definition. So this definition says that element or the transformation T in A of V is called nilpotent. The transformation T is called nilpotent linear transformation if T power of m is 0 for some integer m. Okay. So if T is said to be nilpotent transformation if T power of m is 0 for some m. And also note that if T is nilpotent, okay, if T is nilpotent and if T of V is equal to alpha times V, yes, for some non-zero vector V in V with alpha belongs to F, then alpha should be 0. Alpha should be 0 because T of V, T is nilpotent means T of T itself is 0. So T power of something is 0. T power of something is 0 means, so this will becomes V, since V cannot be 0, the possibility is alpha should be 0. So alpha should be 0 means one class of linear transformations which have all their characteristic roots in F. One class of linear transformations which have all their characteristic roots are in F is the class of nilpotent ones, because all the characteristic roots of nilpotent linear transformations are all 0. Definitely they are lies in the field F. Okay, understand now? So the class of linear transformations whose all characteristic roots lies in a field F is the nilpotent linear transformations. Therefore, we can say that every nilpotent linear transformation can always bring into triangular form, because triangular form existence for the triangular form is, say, all the eigenvalues lies in F. Since all the eigenvalues of a nilpotent linear transformations are zeros which are lies in F, definitely every nilpotent linear transformation can be bring it to triangular form. Okay, yes, let us take up this important lemma. Look here, suppose V is the direct sum of the subspaces V1, V2, etc. Vk, where each subspace Vi is of dimension Ni. These are very important. So each subspace is of dimension Ni and is invariant under T, means each of them are invariant under T, means T of Vi is contained in Vi. Okay, is invariant under T, that belongs to A of V. Then a basis of V can be found. Then a basis of V can be found such that the matrix of T in this basis, the matrix of T in this basis is of the form A1 0 0 etc 0 0 A2 etc 0 0 AK, where each AI is an Ni cross Ni matrix and is the matrix of the linear transformation induced by T on Vi. Understand now? So we have a V here like this. This is V, suppose, okay, not exactly, suppose this is V. So suppose this is the sum of subspaces, say they have 9 subspaces. Okay, say let us take V1, V2, V3, V4, V5, V6, V7, V8, V9. So union of all these VIs is, say, V, and V is the, suppose V is the direct sum of, because 0 should be common to all the subspaces, but this is not, I am against saying this is not exactly the representation of V as the direct sum of these. Okay, so this is equal to V1, SV2 and so on Vn. Now, so T is an operator on V means what? T is a mapping from same. Say this is same. Say V to V to V. T is a mapping from V to V. So here the same subspace as V1, V2, V3, V4, V5, V6, V7, V8, V9. Now T maps V to V because T is an operator. Now V being the direct sum of these subspaces. So definitely T maps every element of V1 to V1 because it is a linear transformation now. Now T on V1, let us say that restricted transformation T to V1 is T1. Are understand now? The restricted mapping of T on V1 is T1. Similarly, the restriction map of T maps this to this means T maps whole of this to whole of this. So if you come to T on this part, that is V1, it becomes T1. T on V2 becomes T2. T on V3 becomes T3. Likewise, T on V9 becomes T9. Are understand now? Okay. So now this lemma says, okay, if V is the direct sum of these subspaces where each Vi is of dimension Ni means V1 is of dimension N1, V2 is of dimension N2, V3 is of dimension N3 and so on. Okay, and they are all invariant under T. Then a basis of V can be found such that the matrix of T in this form where each A is an Ni cross Ni matrix and is a matrix of linear transformation induced by T on Vi. Okay, so let us take up the proof now. So suppose we choose a basis of V as follows. Okay, suppose V11, this indexing is very important here. V11, V21, etc. V first, what is the dimension of the V1? It is N1. So Vn1 of 1, the upper suffix s, upper index denotes the basis or corresponds to the subspace V1. Okay, understand now? These are corresponding to the subspace V1. And similarly, say V1, etc. What is the dimension of V2? It is N2. So upper index denotes, say 2, 2, 2 means this is a basis corresponding to the S subspace V2 and so on. Are understand now? Okay. So this is N1 number of basis elements for V1 because its of dimension is N1. These are N2 number of basis elements because V2 is of dimension N2. Likewise. Now each Vi is invariant under T. Each Vi is invariant under T means what will happen? T of V11 belongs to where? Okay, it belongs to V1. T of V21 belongs to V1. T of Vn11 belongs to V1. Similarly, T of V12 belongs to V2. T of V22 belongs to V2. T of Vn22 belongs to V2. Likewise, all because each of these subspaces are invariant under T. That means if you write in index notation, T of Vj I belongs to where? Vi, because these are the basis. I denotes the S, the number of or the index of the subspace Vi, right? T of Vj means T of 1, 1, 1. Suppose I is this is like T of 1, 1 I belongs to Vi, T of 1, 2 I belongs to Vi and so on. So and is the, now this is the, look here, these are all belongs to V1 means these are all T of V11 is a linear combination of these basis elements. T of V21 is also linear combination of these basis elements because T is a mapping from V to V. Okay, therefore each of the elements, say ith element only we have considered, T of, say T of V11. T of V11 belongs to where? Say indexing, again indexing the scalars is also very important. Alpha 111 V11, alpha 121 V21. Just in the previous case only we have the n number of basis elements, therefore we can make indexing very easy. Here we have n1, each one is of dimension ni means n1, n2, etc. nk number of elements. Okay, so The next is T of V21, alpha 211 V11, alpha 221 V21, etc. alpha 2N11 Vn11. Likewise, say T of Vn11 is equal to alpha N111 V11. These are the bases fixed. Alpha N121 V21, etc. alpha N1 N11 Vn11. Now we have expressed the basis elements T of V1. We are working with V1 now. So the matrix of linear transformation T on V1 is how it looks. So we write about the system of equations in a matrix form, right? So this will be equal to A1. If I call this by A1, alpha 11, alpha 121, alpha 1 N11. Okay. Similarly, alpha N111, alpha N121, etc. alpha N1 into N1 cross N1 matrix. This is a N1 cross N1 matrix. Similarly, I can find A2, A3 and so on. You all collect this. As we get the required form, which is A1 0 0 0 A2 and so on. Okay, understand now? Okay, so A2 is the matrix corresponding to the transformation T on V2. So similarly AK. Okay, understand this? If you want more clarity on this, suppose V is, look here. Suppose V is the direct sum of V1 plus V2. Okay. Now X belongs to V implies how X looks by definition of a direct sum. X is equal to, okay, X is equal to Y plus Z, where Y belongs to V1, Z belongs to V2. Now these are subspaces. Say let us take the basis of V1. V1 is, suppose V1 is of dimension 2 only. Say the basis, or say you take the basis to be V1, V2. First one for V1 basis. Okay, basis for V2 is say U1, U2 for V2. Understand now? So basis for V1 is V1, V2. Basis for V2 is U1, U2. Okay. Now look here. These are basis means these are elements of V1, these are elements of V2, and so they are elements of V only. Okay, understand now? These are elements of V1. One means V1, V2, U1, U2, they are all elements of V only. Since T is a mapping from V to V, look here. Since T is a mapping from V to V, okay, so T of V1 belongs to V1, sorry, V. T of V2 lies between, it belongs to V. T of U1 also belongs to V. T of U2 also belongs to V. Therefore, what are the basis for V then? This is a basis for V1 and this is a basis for V2, means the combination of these V1, V2, U1, U2 are the basis for V, right? Therefore, T of V1 can be written as, look here, T of V1 is equal to, T of V1 is, it lies in V1, but if you take V1 belongs to V, it belongs to V1, so it is a linear combination of basis elements of V1. What is that? Say, I will write alpha 11 V1, okay, plus alpha 12 V2, plus what are the total number of basis elements for V? So 4 number of basis elements, so therefore alpha 13 into, so 0 times U1 plus 0 times what? U2. Okay, one element. Next element, look here, T of V2. I'll write T of V2 is equal to what? Alpha 21 V1 plus alpha 22 V2 plus, right? Say 0 times U1 plus 0 times U2. Okay, Next is T of U1. T of U1 means U1 belongs to V, but U1 actually belongs to V2. Therefore, this can be written as 0 times V1 plus 0 times V2 plus, say, third coordinate is alpha. Say this is alpha. I can write it as 3, 3. Alpha 3, 3 U1 plus alpha 3, 4 U2. Can I write like this? Yes. Next, T of U2 is equal to, again, 0 into V1 plus 0 into V2 plus alpha 4, 3 U1 plus alpha 4, 4 U2. So you write this matrix in the matrix form. It is like, say, alpha 1, 1, alpha 1, 2, next is 0, 0, alpha 2, 1, alpha 2, 2, 0, 0, next is 0, 0, alpha 3, 3, alpha 3, 4, 0, 0, alpha 4, 3, alpha 4, 4. Understand now? This is the matrix. This is one matrix. This is the matrix corresponding to the transformation T on V1. This we may call it as, say, A1. A1, 0. Next, 0, A2. Understand now? A1, 0, A1, 0, 0, A2. So this is the 0 matrix. Okay, understand now? So in the previous theorem, this is of S order, n1 cross n1 order. This matrix A1 is of order n1 cross n1 matrix. This is of order n2 cross n2 matrix, and so on up to k number of there. Understand now? So this is how we obtained the matrix in the previous lemma. Okay, this is the matrix corresponding to, this is the matrix corresponding to the transformation same T on A1, may be called as the matrix of T1, because T is a mapping from V to V means what? V is the direct sum of V1 plus V2. So T from V1 plus V2 means T on V1 we may call it by T1, T on V2 we may call it by T2. So this is the matrix of T1 and the matrix of T2. Okay. Let's take up the next lemma. This lemma says, if T belongs to A of V is nilpotent, then the polynomial alpha naught plus alpha 1t etc. alpha m t power of m, where each alpha is invertible if alpha naught is non-zero. If the leading term, first term is non-zero, then our constant term of this polynomial is non-zero, then it is invertible. Okay, for this, suppose we have a transformation, say S. Suppose S is nilpotent and alpha naught is non-zero element in F. Then you consider this alpha naught plus S is one polynomial into the other polynomial 1 by alpha naught minus S by alpha naught square plus S square by alpha naught cube and so on, minus 1 raised to r minus 1 by SR 1 minus 1 raised to r power of r minus 1 into SR minus 1 by alpha naught raised to r. Okay, so you multiply this. If you multiply this, what do you get? Say alpha naught into this. Alpha naught into this means alpha naught into all terms means alpha naught into alpha naught is 1 by alpha naught is 1 minus S by 1 times of alpha naught get cancelled. So S by alpha naught plus S square by alpha naught square and so on, minus 1 raised to r minus 1 into SR minus 1 by alpha naught raised to r get cancelled r minus 1 plus, so multiply throughout by S by alpha naught minus S square by alpha naught square and so on. The term is minus 1 raised to r minus 1 into SR by alpha naught raised to r. So the terms get cancelled, this term get cancelled, only remaining is 1, because last term also remains, but S power of r is 0 because S is nilpotent. Okay, S power, this is equal to 1 if S is nilpotent means S power of r is 0. The total term, if this only term remains, so the total term is equal to 1 if S is nilpotent or S power of r is 0. Okay, understand now? So now look here, This into this is equal to 1 means what? They are invertible linear trans. This is the invertible to this and this is invertible to this. Say now let's come to our theorem. If t is nilpotent, that is t power of r is 0, and if I take s is equal to, alpha 1 t plus alpha 2 t square etc. alpha m t power of m. If I take s is equal to alpha 1 t plus alpha 2 t square etc. alpha m t power of m, then s power of r is definitely 0. S power of r is 0 because t power, we have assumed that t power of r is 0 means what is s power of r? S power of r means t power of r plus alpha square into t square power of r. T power of r itself 0 means every term will be 0. Because look here, if t square is 0, suppose if t square is 0, then what about t cube? T cube is t square into t, that's also 0. So every term, every power of t after 2 will be 0. Okay, answer now? So now this is 0. Okay, then s is this one. So s power of r is equal to 0. So s power of r is 0. Then this is invertible, means alpha naught plus s is what? Alpha naught, you take s as this, you add alpha naught. Alpha naught means alpha naught plus alpha 1 t alpha 2 t square, which is the required polynomial. Okay, which is the required polynomial. So that is invertible because this into this is nothing but what? Alpha naught plus s is the required polynomial. This into this is equal to 1, means they are invertible if s power of r is 0. Therefore the polynomial alpha naught plus alpha 1 t etc. alpha 2 t square etc. alpha m t power of m is invertible. Okay. Next, look here. So suppose t is nilpotent. T is nilpotent means what? T power of some power is equal to 0. Then k is called the index of nilpotence of t. K is called the index of nilpotence of t if t power of k is 0 but t power of k minus 1 is non-zero. So t belongs to f is nilpotent, then k is called the index of nilpotence of t1 if t power of k is 0 but t power of k minus 1 is non-zero. Okay. So likewise in the previous case, if t square is 0, means t cube definitely 0 but t is not equal to 0. Okay, then we say t is a nilpotent of index 2. T is a nilpotent of index 2. So here t power of k is 0 but t power of k minus 1 is not 0. So let us take up the standard nilpotent matrices. M2 you take 0 1 0 0, definitely this is a non-zero matrix. If you take m2 square is 0 1 into 0 1 0 1 0 0 0 1 0 0, you multiply it, you get 0, means m2 square is 0, m2 not 0, m2 square is 0 means what? M2 is a nilpotent matrix of index 2. Okay. Similarly, take m3 is what? M3 considered to be 0 1 0 0 0 1 0 0 0, which is definitely non-zero. Let us consider m3 square. M3 square again it is non-zero matrix, but m3 cube we consider it is to be found to be 0. Therefore m3, the matrix m3 is an nilpotent matrix of index 3. Likewise we can generalize this as, say in general 0 1 0 0 etc. 0 0 1 etc. Last but one column, one but row is the last element is 0, 1, all others are zeros. So definitely MR is a nilpotent matrix of index R. You can verify this. MR is a nilpotent matrix of index R. These are called the standard nilpotent matrices. These have very huge applications or importance while proving rational canonical forms, Jordan canonical forms and so on. Okay, these are the examples. So in the next class I'll take up another important theorem based on the concepts which we have discussed now. Okay, thank you for listening.